Kenji Suzuki. Ladies and gentlemen, the first agenda of the conference session is keynote speech from the invited speaker, Mr. Kenji Suzuki from Tokyo Institute of Technology, Japan. To moderate this session, we invite Dr. Muhammad Andri Budiman, STMCom, SCMAM, as the moderator for the first keynote speech. Please welcome Mr. Dr. Muhammad Andri Budiman, STMCom, SCMAM.
Thank you so much. Good morning, ladies and gentlemen. Selamat pagi. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Andri Budiman. Let me introduce our distinguished speaker, Professor Kenji Suzuki, who has a PhD from Nagoya University. He worked at several places, such as Hitachi Medical Corporation, Aichi Prefectural University, Japan, as a faculty member. Also in Department of Radiology, University of Chicago, as an assistant professor, and Medical Imaging Research Center at Illinois Institute of Technology as associate professor. He's currently a tenured professor and director of Biomedical Artificial Intelligence Research Unit at Institute of Innovative Research, Tokyo Institute of Technology, Japan. He has published more than 350 papers, and he has been actively researching on deep learning in medical imaging and AI-aided diagnosis in the past 25 years, especially in his early deep learning model was proposed in 1994. His papers were cited more than 13,000 times, and his age index is 55. Professor Suzuki, you may start the talk now. Thank you.
Thank you very much. Let me share my slides. It seems that I can share my slide. Can you? Okay. Can you see my screen?
Yes, Professor.
Okay. Thank you, Professor Budiman, for the detailed introduction. I will talk about today AI doctor and medical AI imaging with deep learning. Let me introduce myself a little bit. As the introduced, I worked at University of Chicago for 13 years and then Tech for 4 years. Then I moved my AI lab for medical imaging from Chicago to here in Tokyo, Japan. That was 2018. I was invited to join Tokyo Tech through World Research Hub Initiative, which is an initiative that recruiting top researchers from all around the world, and I was invited in AI field. The gentleman next to me is Professor Osumi, who won the Nobel Prize in Medicine in 2016. He's one of the members of the initiative and the most successful case. So, as you know, deep learning obtained enthusiastic attention as a breakthrough technology from academia and industry. Some people said AI driven by deep learning would make the fourth industrial revolution. When you say the fourth industrial revolution is not the matter of an individual or researcher, it's a matter of the country. So the many countries treat AI as the strategic research area. And also the index for it, insurgent attention from business side. This is global market prediction. Global AI market in healthcare is expected to reach at $66.8 billion in 2027, with an annual growth rate of 100%. So it is one of the most rapidly growing, promising areas in AI. So the conference is AI in medical imaging area. Those are top conferences starting from ICCAI, ISB, EMBC, and MLMI. MLMI is a machine learning in medical imaging. That international conference was created by myself and my friends in 2010. And then it continues, and this year is 12th one. And also, I'm still a little bit talk about myself. I'm associate editor and editor-in-chief of journals like this, and in mostly AI, computer vision, and medicine area. So this is kind of summary of my lab research history. Since 1994, my lab has been studying actively on deep learning in medical imaging, including the first FDA-approved deep learning product. I will introduce some of them today. So my contents today has two major topics. One is AI-aided diagnosis with medical images, or AI doctor. And the other one is virtual medical imaging with deep learning. The first topic is, it used to call the computer-aided diagnosis, but now people call AI-aided diagnosis or AI doctor. This is a definition of computer-aided diagnosis, or CAD or CAD, may be defined as diagnosis made by a physician who takes into account the computer outputs as second opinion. So it's like this. You have medical image, you put medical image into computer AI and it analyzes it. And then the AI tells you I found a pattern similar to cancer, look at this. And then you, as a physician, make a final diagnosis by using AI physician as a second opinion. This is the concept of computer-aided diagnosis. There's another important, similar but different concept, which is automated diagnosis. In automated diagnosis, AI diagnose itself without humans. And it's like driver assistance versus automated driving. In driver assistant, your car gives you alert the person is walking in front of your car. Whereas in automated driving, your car drives itself, and you can read newspaper in a car. So that's the difference between the two. Computer-aided diagnosis is similar to the children's book called Where's Waldo. This is Waldo. Your task is to find Waldo from this complicated scene. So can you find Waldo? It might be difficult because the spatial resolution is limited. The contrast resolution is limited. Maybe it's noisy. More importantly, there are patterns similar to border that makes you to find a border instantly. Take a little time to find a border from here. And then if you find it, or maybe you still looking for a border, let's ask AI for help. So AI said, this one will be a border, and this one might be border. And the truth is, the first one is real border. So it's called a true positive. And then second one is not border. So it's called false positive. So keep in mind that the AI can make a mistake. And it's important to keep in mind there's an essential difference. Whereas border has always one border in each two-page spread, whereas there are abnormality only occasionally in medical images. Remember, most cases are normal in screening population. Now, can you find border? Then we need the AI's help. Let me talk a little bit about actual computer-aided diagnosis system. This is CT scan of the lung. Your task is to find lung nodule, which is potential lung cancer, from this image. Before deep learning, we do these steps. So there are 4 steps, and I will show you each step one by one. In the first step, you segment the lungs or organs so that you can focus on the lungs. And then second step is detecting nodule candidate and segment them. So in this stage, there are many false positives, computer mistakes. And then to remove false positives, in the third step, we calculate features from each island, such as contrast area, circularity, and so on. And then fourth and the final step, machine learning comes to play a role. So the to distinguish from deep learning, it's called feature-based machine learning. The inputted features extracted from segmented object, and then what the feature-based machine learning does is to determine the decision boundary between nodules and non-nodules, so that when the unknown candidate comes, and you can the AI can distinguish between the two. So that is the steps that we always took before deep learning. This is history of machine learning and computer vision. The upper is the feature-based machine learning, and the lower is the deep learning. The deep learning in 2012, it became very popular and created the AI research boom. But deep learning has long history, actually. I will let you know, talk a little bit about our original deep learning model shortly. So with that feature-based machine learning, we applied to evaluate the performance of the feature-based machine learning. We applied it to this database. this database is unique because that contains 38 lung cancer missed by radiologists. So it's very difficult database. And we have 4 steps I explained, and then the performance is like this. The sensitivity, this is correct detection rate of cancer, is 88%. It's not too bad, but when you look at false positives, computer mistakes, there are 16 false positives per patient. It's probably too many like this. So we need advanced method, advanced machine learning to reduce those false positives. And this is the explain why deep learning is breakthrough from the aspect of amount of data. I borrowed this from the slide by Andrew Ng at Stanford. When you use a traditional feature-based machine learning AMRED, as the amount of data increases, the performance goes up once but saturated, whereas deep learning's performance going up exceeds the user requirement or human performance. That's why the deep learning is called breakthrough. And then we have to reduce the false positives. We have original deep learning model called MTANN back in 1996. So what is MTANN? That is a massive training artificial neural network. It's called MTAN, and it's supervised image processing based on machine learning. And MTAN directly down the relationship between input images and the corresponding ideal image called teaching image. And to enhance specific pattern, in this case, lung cancer is here, so you can train MTAN to enhance lung cancer like this. This is the architecture of MTAN. MTAN's input is the pixel values, pixels in a sub-regional image patch extracted from input image. The output is a single pixels. So unlike deep learning, other typical deep learning models, the output is the pixels, not categories such as cancer or non-cancer. To train and process the entire image, the scanning or convolutional operation is performed like this. However, unlike convolutional neural network, convolution is done outside the network. That is the difference between the two. And in training, we have image patches, and then we get the output of the pixels. We compare them with teaching pixels and calculate the difference. And to minimize the errors, we adjust weight. So after training, the output pixels is expected to similar to teaching pixels. So going back to the false positives, we have lung nodule on the left and the false positives on the right. We have to distinguish between the two. The major source of false positives is best cells because lungs contains best cells and air. To reduce false positive or distinguish between the two, we train MTAN like this. We prepare a teaching image that contains wide Gaussian distribution at the center of lung nodule, and then that for non-nodules is completely dark. So we train MTAN to enhance lung nodules and suppress best cells. when we apply the trained MTAN to lung nodules, we get the output images like this. Remember that the output of MTAN model is images, not categories such as cancer or non-cancer. So the output of these images, as you can see, that lung nodules are enhanced nicely in the output images, whereas those for lung vessels are completely dark in the output images, or lung vessels disappear in the output images. For other patterns, the MTAN was able to erase those patterns in the output images. So once the MTAN enhances lung nodules and suppress other patterns nicely, and then the distinction between the two is performed in a scoring layer, we just calculate the output image, multiplying output images with Gaussian weighting function to calculate a score. So higher score will indicate lung nodule and lower score, no nodules. This is the performance sensitivity versus number of false positive per patient. We started from 16 difficult false positive per patient. By using MTAN, we were able to remove 88% of false positive without reduction in the number of true positive, and achieved 1.9 false positive per patient. So this is done for small regional interest, but like this, but we can apply this MTAN to the entire CT image. To do that, we prepare the teaching image like this. So input is entire CT image, and a teaching image contains wide Gaussian distribution, the location of lung nodule, and rest of the areas completely dark. And then we train MTAN and apply to the unknown image. So here's the lung cancer, but it's very difficult to detect. Actually, the radiologist missed this lung cancer. This is the output image. You can see that lung cancer is enhanced in suppressed lung vessels. There are white island little bit, but when you threshold it and remove big area and small dot, and then we get this. So this is the perfect computer-aided diagnosis. The lung nodule is detected without any false positives. So with this kind of deep learning model, we can condense those 4 steps into 1 step from start to end. And then that's why it's called end-to-end machine learning paradigm. So we get the attention from media. So you may be wondering that what about the other deep learning model? So as you know, that deep learning model has a deep layers. The input is the images, so the same as MTAN, but the output is usually labels. So that is the difference. For our deep learning, the issues, deep learning is a wonderful, wonderful technology, but there are some limitations. The bottleneck of deep learning, particularly in medicine area, is necessity of huge amount of data. So this is the paper published in Nature in 2017. It reported that deep learning performance was equivalent to doctors in diagnosis skin cancer when it was trained with 140,000 images. 1.4 million images actually. However, the problem is that in medicine area, collecting such large number of cases is very difficult, and it takes years. Once you collected, you need to ask doctors to annotate and label it. That is the huge burden, and that is the bottleneck of deep learning in medicine area. To reduce the issue, we have transfer learning. In transfer learning, you train your model with large number of images in a different area, and you transfer the model or weight and fine-tune the model with smaller number of the medical images. However, with this method, even with this method, you need still 130,000 medical images. It's huge. So with that issue, we need this. So we need deep learning model that can be trained with small number of cases, and I named it small data deep learning. So even with small data, not big data, the small data deep learning model exceeds user requirement. That is the what we needed in particularly the medicine area. And then the question is it possible to develop a deep learning model that does not require 100,000 cases? And our MTAM model has such nice property. We compare MTAM with CNN's other deep learning model in the lung cancer detection problem. So we compare with 5 representative CNN model, including AlexNet and Google LUNET. We train the 5 CNN model with a small number of cases and tested on the same database, unknown, but the database. And this is the performance. The blue one is MTAM performance. This is sensitivity versus number of false positives per patient. And the other curves are 5 different CNN model. The best one is fine-tuned AlexNet, the AlexNet with transfer learning. So when we extract it, this is the best CNN model that achieve 24% sensitivity for detecting lung cancer, whereas the MTAM got 100%. So this both MTAM's performance is high because we trained those two models with only 100 samples. So the MTAM is robust and the high performance in the small data area. And then now, the next question would be, what is the minimum number of cases trained in MTAM? To test this, we use this program. We use semantic segmentation of liver cancer. So this is the CT image of liver, and the task is segment the liver tumor, like radiologist does. And there was a world competition in 2017. This is a list of top teams. The best one or winner is this. from Lenovo, and that is coefficient is performance indices. And the number of training tumors, they use 900 tumors for training. And we compare our MTON with those competition winners. This is the architecture of 3D MTON. We have Hessian enhancer here, and a teaching image is something like this. We have liver tumor segmentation by manually and train the MTON model. And to evaluate the performance, we use dice coefficients, that is basically overlap area between true area versus predicted area. And we increase the number of training tumors from 7 to 14 to 28 and so on. And this is the result. The red one is gold standard manual segmentation by radiologist, and the green one is MTON, and yellow one is complete agreement. So as you can see that the MTONs, the semantic segmentation agree well with gold standard. And then this is the summary of comparison. So when we train MTON with 7 tumors, the dice coefficient was 0.69, and we increased to 14 tumors, and then our MTON achieved 0.70. That is equivalent to the competition winner. So we were able to reduce the number of training cases a factor of 65. And this is the summary of advantages of MTON over other deep learning model. The first, the important advantage is MTON can be trained with small number of cases. The another important thing is the computational cost is very low. You can run the or train the MTON model on a laptop. Does not require GPU server. So with the MTON model, we can build small data deep learning model. This is the first part of the topic, and the second part is the virtual deep learning or AI imaging. I created this term. There are 2 topics. One is about chest radiograph, and another is about CT. So the definition of virtual deep learning imaging or virtual AI imaging, this is my definition. So AI imaging may be defined as imaging for visualizing, enhancing physical or semantic object and or materials by using deep learning regression. And the goal is to make the invisible visible, or the less visible more visible. The first application I introduced is the chest radiograph. So this is a toy problem that related to the problem that I will talk about in shortly. So there are overlapping characters, and can you find a lesion from these overlapping characters? Please take the time to find lesion. It is difficult because of the overlapping. However, if we remove those overlaps, and then you can readily find lesion. Actually, there are 2 lesions. In one study, famous study by Austin, they reported more than 80% of the lung cancer missed by radiologists overlap with overlap with bones. So if we can remove those overlaps, we can avoid those misses. So our goal is to extract ribs and clavicles from chest radiograph. To do that, we have specialized equipment called dual energy subtraction imaging. In this imaging, you expose two X-rays to the patient, so that X-rays twice. One is at low energy level, one is at high energy level. We get two images, and subtracting with those two images with smart algorithm called dual energy subtraction algorithm, we can obtain soft tissue enhanced image and bone enhanced image. This is wonderful system, but there are limitations. First one is specialized equipment is required. More important, radiation dose to patient can be double. So if we can do the same thing with only software, that would be great. So the question in this study is, can we separate bones from soft tissue in chest radiographs by only software? To do that, we used MTAN. As I mentioned, the MTAN's output is images. You can train images. So in training step, we use the dual energy system. So input images is standard chest radiograph with overlapping bones. And for teaching image, we use dual energy soft tissue and bone images. And we use multi-resolution MTAN. The multi-resolution MTANs look like this. They divide original full resolution images into multiple scales, and then apply the three different MTANs, and then reconstructed back to the original one. So this has U structure, and we didn't call it UNet, but there are somebody reinvented the similar network and called UNet is here. So multi-resolution MTAN is similar to UNet, but the proposed long time ago. And we use the UNet type multi-resolution MTAN. Basically, we once trained, we don't need dual energy system anymore. We can apply the trained MTAN to single image from the standard system to obtain soft tissue and bone images. Here's a result when we apply the trained MTAN. As you can see, ribs and clavicles are suppressed while maintaining soft tissue such as lung vessels. This is side-by-side comparison. The MTAN soft tissue image is on the right, that is created from the original image on the left. And this is bone enhanced image. Bones are determined well. This is comparison with real dual energy soft tissue image on the right. You see that those two images are very similar. When we enlarge them, the MTAN soft tissue image is in the middle, created from image on the left, and that is similar to the gold standard dual energy soft tissue image on the right. So in other words, this to create this image, the patient get two X-ray exposures, but not but single when we create MTAN soft tissue image in the middle. This is cancer case. You see that lung cancer overlap with rib. When you take a look at the MTAN soft tissue image, conspicuity of lung cancer is enhanced, improved by removing overlapping bone structures. So with this technology, we don't need specialized equipment or no additional radiation dose to patient, but we need only software. And we get some media coverage. And this technology was actually commercialized by a startup company in the US. University of Chicago licensed the technology to the company, and they obtained FDA approval in 2010. That is when we go back and think about the event that actually this is the first FDA approved deep learning product back in 2010, before deep learning boom started. One more topic in AI imaging is about CT, which is radiation dose reduction in CT. Our purpose was to develop a new MTAN technique for converting low-dose CT images into high-dose light images to reduce radiation dose in CT. So to do that, we need the ultra-low-dose CT image and corresponding high-dose CT image pair from phantom, not patient, to train MTAN. Once trained, we don't need high-dose image anymore. We can apply the trained MTAN to new ultra-low-dose CT image of a patient to obtain high-dose CT light image where noise and artifact are reduced and with the images are high quality. So this is the result. The image on the left is the ultra-low-dose CT image with 0.2 millisievert. This is the lowest limit of CT scan. As you see, that noise and artifact are very heavy, and then lung nodule. Here's a lung nodule, but it's difficult to identify. When you increase the radiation to 10 times and you get this image on the right, the noise is reduced, but still a little bit noisy. And the image in the middle is a virtual high-dose CT image with MTAN technology. As you see, that the nodule is very clear, you can identify it, the noise and artifact are reduced, and you can see that the vessels, even if they are small. And then when I asked radiologists to evaluate the image quality, they said the image quality of MTAN is higher than this high-dose image. That is because we trained MTAN with a very, very high-dose image of a phantom, wider image of a phantom, 35 millisievert. When we do quantitative evaluation, the 0.2 millisievert image is equivalent to 7.34 millisievert image. That means we can remove 97% radiation dose. And 97% radiation dose is the very high compared to existing state-of-the-art radiation dose reduction technology, that can reduce only 17 to 44%. And the computational time is minimum. You can run our MTAN on a laptop, and it takes only 20 seconds for 600 images, to process 600 images. This technology was actually commercialized by a startup company in Bay Area, Silicon Valley in the US, and they get FDA approval in 2016. Because the times is up, I will skip this. Basically, you can apply the same technology to mammography, X-ray images, and then you can do semantic segmentation by using MTAN, you can get the semantic segmentation results similar to the doctor's segmentation. So in conclusion, deep learning AI is a rapidly growing area of research in medical imaging. And I introduced AI-aided diagnosis. The issue is small data, big data issue, and we need to develop small data deep learning, and we developed the MTAN for that. And I introduced deep learning or AI imaging that can remove bone component from chest radiographs, or you can create virtual high-dose images in CT. Thank you for your attention.
Thank you so much, Professor Kenji Suzuki, for your interesting talk about deep learning, especially MTAN. Your talk has clearly shown that massive training artificial neural network of deep learning is having the higher performance than older learning algorithms and can even exceed the user requirement. What more is interesting is that this can be done even with smaller data. So I would like shall invite some questions from the audiences. Is there any questions about Professor Suzuki's presentation? Okay, there's one question from Mr. Ivan Jaya. So the question is, in general, for image identification or classification, how much data is needed for deep learning algorithms to process? Is feature-based machine learning like SVM still worth using? Then the second question is, M10 can work on small amounts of data. What is the minimum amount of data that M10 can process with good accuracy?
Thank you for the questions.
Yeah.
So the other deep learning model, let me change slide. Let me find one. So the usually it's said that deep learning model requires 10,000 to 100,000 cases for per disease, and when you use transfer learning, it can reduce to 130,000 images, but you still need 130,000 images. Whereas MTAN need small data, and for this lung cancer problem, we needed 100 cases, not 130,000 cases. And the for feature-based machine learning, not deep learning, the required number of cases is smaller, such as 500 to 1,000. But the performance does not exceed the human performance or the user requirement. That was a problem, and then deep learning called breakthrough because it exceeded the human performance. But when big data is available, that is the same. And for the second question, the minimum number of cases to require training the MTAN, we did this the problem, and the results show that the minimum is the 14 tumors, so less than 20, to reach the world champion performance of 0.70 dice coefficient. So the minimum number of cases trained MTAN is something like 10 or 20.
Okay, arigato.
Arigatou gozaimasu.
Okay. Is there any other question from the audience? Okay, I have one question from myself.
There's one question from me.
Okay, there's
maybe
a question from Mr. Amir Saraj. Yeah,
on the
please.
chat. Or do I ask directly, or
You can ask directly.
Okay.
Yeah.
Oh, okay then. Okay, thank you, Mr. Andre, for the opportunity, and thank you, Professor Suzuki, for the wonderful presentation. It's very mind-opening for what you presented, how much advance that has been reached in this area.
Thank you.
From what I understand from your presentation, it seems that one of the key aspects in MTAN is providing the teaching image. It seems, Prof. Suzuki. So, how do we provide these teaching images? Are they do we get them from the similar case or similar disease and then process somehow, or maybe you can shed some light in this aspect? Thank you, Prof. Suzuki.
Thank you for the questions. So basically, the teaching cases is images, not category. Like other deep learning model, you just need the which one contains cancer, which case contains cancer, which image contains cancer. But for training MTAN, you have to prepare the images because the output by images, output by MTAN model is images. So you have to teach MTAN with somehow the images to enhance or detect or segment object. You put white distribution or white thing in the teaching image to enhance the specific object. In this case, lung cancer. When you train MTAN with this teaching image, the MTAN learn to enhance lung cancer and suppress other patterns. And then by using this, you can obtain the result like this. You can segment lung cancer nicely without any false positives. And more specific application, not just a distinction between cancer and non-cancer, such as semantic segmentation. You use the cancer segmentation by doctor like this, and you train the MTAN model manual segmentation like this. This is small, but it's actually manual segmentation by radiologist, similar to this, and then once trained with those images, you can get this wonderful result. And then you can train the MTAN with very small number of cases.
Okay, so basically, if I may continue a little, Mr. Amri, perhaps. Okay, so basically the teaching image comes from another image, perhaps with the same disease, but already enhanced, something like that, Prof. Suzuki.
Yeah. So basically, this is the computer generated image.
A computer generated image, yeah. So it doesn't have to be from the same disease. Just if you want the MTAN to look for like some bright areas, then we use like it doesn't have to be an image from the disease process. Basically, it's just what we need the MTAN to look for in the image, like some white bright area, something like that.
Yeah, any object or any images can be trained. So basically, when you have say car or person, and then you need to prepare the input image of the car, and then the teaching image is the car shape image, and then train.
Okay, I see. Thank you very much, Prof. Suzuki, for the enlightenment.
Thank you very much.
Okay, arigato, Professor Kenji Suzuki. I have my own question about the M10, Professor. The M10 virtual dual energy doesn't seem to need the specialized equipment and doesn't need additional radiation dose to patient, and it only needs software, which is outstanding. So my question is, has it already been approved for clinical use since it is not very easy to get approval from the health department?
Yeah, so that is the answer is yes. We developed this technology, and by using MTAN, we can remove one component from chest radiograph, and then as a researcher in academia, we cannot get the government approval, such as FDA approval. The company who get the license from us, they commercialize it, and then tested with the many patients, and then they get the approval. And it's actually implemented in many hospitals in the world by today.
Okay, thank you so much, Professor Kenji Suzuki. The committee, the dean, and the vice rector would like to give a certificate to you. Please, the operator, prepare the certificate.
Oh, that's nice.
Yeah. Okay, thank you so much, Professor Kenji Suzuki, for the contribution as presenter of the paper entitled AI Doctor and Medical AI Imaging with Deep Learning at the 6th International Conference on Computing and Applied Informatics 2020, a new world of research, sustainable research in digital world. Medan, Indonesia, 8th of November 2022. This certificate is given by Dr. Maya Silvulidia, which is the Dean of the Faculty of Computer Science and Information Technology, and Professor Opi Alzed Hasibuan, which is the Vice Rector of Research, Community Service and Cooperation, Universitas Sumatera Utara. Once again, thank you, and I would like to give an applause for your presentation.
Thank you very much.
Thank you
I
so
really
much.
appreciate it.
Yeah, arigatou gozaimasu.
ありがとうございました。
Yeah. Okay, thank you so much. I shall give the floor back to the Master of Ceremony. See you again, Professor Kenji Suzuki.
Thank you very much.
Thank you, Mr. Kenji Suzuki, for your exceptional speech, and Mr. Dr. Andri Budiman, STMcom SCMAM, for your help to organize this session. Ladies and gentlemen, our next keynote speech will be held by our second invited speaker, Mr. Johannes Cronjé from Cape Peninsula University of Technology, Republic of South Africa. To lead this session, we invite Mr. Amer Sharif SSE MCOM as the moderator for the second keynote speech. Please welcome Mr. Amer Sharif SSE MCOM.
Okay, thank you, Master of Ceremony, for the introduction. Yeah, good afternoon, good morning, everyone. I'm very pleased to have you all here. And also, we are very distinguished to have the presence of our next keynote speaker, Professor Johannes Cronjé. I hope I pronounce your name right, Professor. Before we begin, please allow me to read a short introduction of you that I simply take from your Google sites. Okay, so Professor Cronjé has a very fascinating background. He is a professor in digital teaching and learning in the Department of Information Technology at the Peninsula University of Technology, Republic of South Africa. He was before that he was Dean of the Informatics and Design, and has supervised more than 140 masters and doctoral students and published more than 65 peer-reviewed papers. So we are very fortunate today to have Professor Cronjé among us to share his knowledge. And I see that he has also shared the link to his sites at Google, and which is I find quite fascinating because he shared a lot of his work there, including some YouTube videos about writing proposal research, and even one writing a research proposal like a fairy tale. I would like to see that later, perhaps. I think that would be very fascinating to follow, and also for my colleagues at the PhD program here at Faculty of Computer Science and Information Technology. So, and also Professor Cronjé has shared a lot of his works there, and I think after we enjoy his presentation later, maybe we all can see much closer. But for now, I think let us hear first from Professor Johannes Cronjé, the presentation that he will share with us. So without further ado, Professor Cronjé, the floor is yours.
Thank you very much, Professor Amer, for those very kind words of yours. And I must pay absolute tribute to Professor Suzuki. What I saw now was absolutely mind-boggling. It was brilliant. It gives me so much hope going forward. But what I also saw from him, Professor, you taught me something methodologically. There was one slide where you had a whole lot of words put over each other, and two of those words were lesion. And you showed how you could peel off everything until then eventually you could see those two. And for me, as an educator, as somebody who's been working in teaching and learning all my life, seeing something like that, where something highly complex is made so easy to understand, that's inspiring to me. So I'm going to remember that for a long time. Thank you very much, Professor. But also thank you for the work that you're doing that actually saves lives. So this conference is clearly very well curated, because you went from really, really hard science, and then you got me. And I do the opposite of really, really hard science. I do what is fuzzy. So computer scientists work in a world where there is naught and there is one. And Bart Costco, in a book called Fuzzy Logic many years ago, explained that for a computer scientist, there is an apple or there is not an apple. But from when you start eating the apple until you have eaten the apple, there's a whole lot of things that computer scientists are not interested in, because for them, there is an apple or there is not an apple. I work in that field in between the apple and the not apple. That's where the humans are. And I am really interested all my life in the humans and the technology. And so what I discovered quite recently, actually, is that we've lived in this world where many, many, many years ago, and this is the work of Yuval Harari. I will put these things in the chat if I remember. So Harari pointed out that thousands of years ago, about 30,000 years ago, until very recently, really, but starting about 30,000 years ago, we believed that nature was in charge. And we had all to be subject to nature. We had to listen to nature. We had to obey nature. And to show how well we were obeying nature, we would even sacrifice to nature. We would throw a virgin into a whirlpool, hoping that the water will continue or so. We really tried. Professor Sharif, I must thank you very much for keeping your face here. It is really nice to get some visual reaction and to see that it is working here. You know, it's, I'm looking now, it's 5:45 in the morning down here. So it's quite fun to be so far and yet so close, both in time and distance to you over there. Anyway, so we thought that nature was in charge. Then came the Enlightenment in about the 1800s, and with that, the Industrial Revolution. And suddenly we discovered that actually we human beings can take charge. We can build machines, and with those machines, we can take charge. And that's what we did. And we started forming a very close liaison with the machine. And what Professor Suzuki has just shown us is how we were able to take that machine and train that machine and make that machine a part of us. Now, what we know from the movies is that when a human being and a machine gets connected in such a way that they are parts of each other, we call that a cyborg. And what's happening now is that we have the human beings and the machines connected all the time, even if it's just because we all have this device. And I'm not showing you the name, but anybody will know it's a Samsung. But because we all have that device, we are all connected to everything all the time. And so we learn from one another. And what's really been fascinating me, which is why I really liked the previous speaker's presentation, is that I'm learning a bit from this machine. But this machine is learning an incredible lot from me. And all it costs me is a little bit of privacy, or maybe all my privacy. Or maybe it's not costing me my privacy. Maybe it's costing me what I thought was my privacy. So that's just a little bit. So then the cyborg was running the world. And then something fascinating happened in November 2019, when nature staged the biggest comeback that any ruler of the world had ever staged before. As I said to you, many years ago, we had the whirlpool, the sun, the moon, we worshipped all of them. In November 2019, we started worshipping only one thing. And that was an invisible thing called a virus. And the virus said to us, I'm going to make you only one commandment. The Christian God has 10. Other religions have even more gods, but I'm going to make just one commandment. And that commandment is stay away from each other. And if you don't obey my commandment, I will kill just enough of you to scare the daylights out of you. And that was the commandment. And what happened was that every world leader ever, every religious leader, every person in charge everywhere in the world said, we subject to this new God called COVID-19. And then, because we are humans, we said, we're not going to do this. We are actually going to fight back. And what are we going to do? We are going to use the machines to fight back. And so what we did was we all went to our houses and we all started teaching online, and we started having online conferences, and we started using AI to start looking for a solution to the virus. And so we use technology in record time, quicker than it's ever happened before, to make an antidote to this virus. It took less than 2 years, and we were sort of back on top. So that was interesting. We have a virus attacking humans. We have humans using machines to counterattack the virus. And then what happened? The machines started saying, wait a minute, we're going to use the virus to attack the people. And so the machines, using their very careful algorithms, started saying, let's divide. This is how you rule. Remember the system, divide and rule. And the machine said, we will rule by division. And they divided us into the vaxxers and the anti-vaxxers. And they divided us into the Trumpists and into the anti-Trumpists. And they divided us into the conspiracy theorists and the anti-conspiracy theorists. Why? Because they were looking for the new currency. And some of you will tell us that once upon a time we had gold as a currency. And then we had the markets as a currency, where you could have the financial market and that decides which way you go. And then some of you will tell us that our current currency is Bitcoin or digital currencies. But ladies and gentlemen, we've shifted beyond Bitcoin as a currency. The only currency we have at the moment is the currency of attention. That's what we crave. And the machines want our attention. And so the machines split us into two camps, so that this camp fights with that camp, and there's the attention that the machines get. And what do they get from that attention? Data. But data is just the coinage that underlines the currency of attention. So that's how, in my very deranged mind, the world works. And so I've been struggling to make sense of all this, because as a professor of learning, I was once asked, what is the definition of learning? And I was very scared, because as many professors of education there are, so many definitions of learning you will have. And so I was really concerned about what my definition were. And then I was lucky, the other person actually told me his definition instead, which is learning is being able to do something afterwards that you couldn't do before. And if we look at what the machine learning algorithms showed us, that's exactly what happened. First, the machine couldn't detect cancer. Then we exposed it to 30,000 images, and then it could detect cancer. So the machine couldn't, it learned it could. And so that definition works very well to me until very recently. Because in my family, we have a tradition, something that we all do, and that is we get lost. When we drive somewhere, we budget additional time so that we can stop and ask for directions 3 or 4 times. That's how we go to places, because we always get lost. But then something happened about 10 years ago. I downloaded a program called Waze. I believe it's called Wazi where you are. It's spelled W-A-Z-E. And ever since I downloaded that onto my machine, I stopped getting lost, because Waze would just take me there. It would take me there with the prediction of 1 minute over 30 minutes. Say, you'll be there at 7:29, not 7:30, 7:29. And at 7:29, I would be there. So I could do something I could never do before. But there's been no change in the algorithm. And this was problematic for me. This made me lie awake at night, which is, I thought learning meant that you make a change in your brain. But here, I just put a new app on my phone, and now I can do a whole lot of things. And then I discovered through, and I remember his name in a while, but I discovered that I'd been looking for learning in the wrong place. I'd been looking for learning between my ears. Whereas in fact, learning moved. Learning no longer sits between my ears. Learning sits between our ears. So because Waze has been learning where I go, it can take me more easily to where I want to go. Because Waze has been learning where other people go, it can tell me where the traffic blocks, the roadblocks are. Because Waze has been learning a whole lot of other things, it simply means that the whole system is what is learning. And so that then changed my mind, and I thought, but how do we describe this system? And then I came across the work of Deloitte and Guattari. Prof, you can share a presentation if you wish. Yes, I will when I get to actually the time where the presentation is. I'm still doing the bit called introduction. If somebody could just put in the time when I must stop as well, because my talks work like an antenna. I can pull them out and I can push them in again, depending on what's happening. So if somebody can just put in the chat what the end time will be that I'll know, then I can plan ahead a little. But yes, I'm going to share. I'm not going to share a presentation because I decided that I'm an enemy of PowerPoint. So what I will be sharing instead is my journey, and I'll be showing you some random things in my mind. So what happened to me is I discovered rhizome theory from Deloitte and Guattari. And rhizome theory was about 1990. And to show you rhizome theory, let me share my screen now so that the journey can start. So if you want to know about rhizome theory, and by the way, if you ever tell anybody that I did this, I will deny it. Even if you play them the video, I'll say it was a deep fake. And I must share this screen with you. Great. I'm sharing that screen with you. And just share for sound too. I'm sharing this screen with you because I'm wanting to show the only thing for which a branching tree is useful is that it tells you who signs your leave form, because that's the person above you on the tree. Anything else doesn't work because you have connections way above and beyond and around those various aspects on your tree. So I want to take you through, and I want to make this interactive, and I'm going to take you through how I have used rhizome theory to help me explain the underpinnings of what is going on. And so where the Professor Suzuki's talk was about how to predict cancer, I'm more about how to sort of try and figure out all this fuzziness that's going on around us, and what can we trace, and what can we look at, and so on. And so for that, I have a little form that I want you to fill in with me as I go along. And to get to that little form, you need to get to me. And that's why I posted my website address for you.
Recording in progress.
Form. So there's the form, and I'd like you to fill that in with me. So the rhizome theory says we are not a branching tree. We are like a ginger plant. And so if we go to this rhizome here, I'll show you examples. There you can see it's like a plant that has all its roots. It's an underground stem, and it's got all these roots connected, and everything is connected to everything else. And they say that is much easier than to have a tree describing how the world works, is to have a ginger plant or a mushroom or something like that. Mushrooms are really good examples of rhizomes because they live underground, they hide away. When conditions are good, they pop out, and when conditions are not good, they disappear again. So they are my favorite plants as far as describing the rhizome is concerned. So we're going to have a look at 6 characteristics of the rhizome, and then I'm going to ask you, whoops, where are we? I'm going to ask you, if you put an identifier there, any name, that's fine. If you put an email address, I might just put you on my mailing list. So be careful, you've been warned, your private information. And then I'm going to take you through these 6 characteristics of the rhizome, and I'd like you to vote saying, nope, I see nothing of it, or 5 saying, yes, I see this all the time. So those are the 6 characteristics of the rhizome. And just as a professor of education, for those of you who are interested, you know, we human beings can't remember more than plus minus 5 things. And there are 6 elements of the rhizome. So I can't remember them. But what I can remember is 3 pairs. And those 3 pairs are connectedness and heterogeneity, multiplicity and rupture, cartography and decalcomania. So this is something for you if you're in education at all. Instead of teaching 6 discrete concepts, teach 3 pairs. It's just so much easier. And people can actually remember. So the first thing we're going to have a look at is connectedness. And rhizome theory says that absolutely everything is connected to absolutely everything else. And just to give you an example of that, in my house, I have an electric meter that measures my consumption. And that meter was installed in my house somewhere in the 1940s. So it's 70, 80 years old is my meter. Once a month, I take a photograph of that meter and I WhatsApp that meter to the municipality. And the municipality enter that into a spreadsheet or into a program, and it sends me a bill. And why it does that is right in the middle of my meter is a little number engraved on an aluminium plaque. And that number, the municipality knows its GPS coordinates. And therefore, the municipality knows exactly where I am and what electricity I'm using. All they need is that number. And so in that way, a 1940s style analog device has become an integral part of the Internet of Things and sends me bills once a month. The mind boggles the power that the Internet has given a very simple ancient machine. It now rules at least about 10% of my life is ruled by a little analog machine that deviously works with the municipality. So that's what I want to explain to you about connectedness. Don't think that an old electric meter from the 1940s is irrelevant because it's not on the internet. It can get on the internet in a very simple way by making an old professor take a picture of it. And there it is on the internet. So what I'd like you to do is, in your own thinking, in your own work, in your own environment, to what extent do you find connectedness? And I also discovered something really fascinating the other day, and that is called, which one did I use? Dolly. I don't know if you guys are familiar with Dolly. So Dolly is drawing software. It's much the same as this. So what we could do is I actually set something up here with Dolly. I looked at connectedness. And let's ask it to draw us a picture of connectedness. Come on. Oh, I've reached the end of my history. I can't do anything more with Dolly. So that's all right. I've just shown you this one anyway. So this is what I drew for you using AI. I just typed the word connectedness in, and that's what I got. So the next one that we're going to look at in our rhizome is heterogeneity. Heterogeneity means everything is different from everything else. And we recognize things because of their difference. And this is what OpenAI says to me what heterogeneity is about. Isn't this the most beautiful rendition made by the AI of heterogeneity? They're all eggs, but this egg is different. They're all eggs, but this egg is different. But if you look at that heterogeneity, it's been drawn so smoothly, and yet one is the bottom one, the other one is the top one, the others are part of a little cluster. If you look at this over here, here's a little, come on, man. There's a little close cluster, and then there's a looser cluster. So everything is different from everything else. You just need to go and look for those differences. And then it takes it from these blue things to the eggs, and then it takes it across to the ivies. So even in nature, heterogeneity is just always present. And so again, my challenge to you is, to what extent are you noticing and are you exploiting and are you looking for the differences? And one of the things one has to remember with connectedness and heterogeneity is that they are connected. You can only connect things when they are different. You can't connect the same thing to the same thing, then there isn't connection. So you have to have things that are different when they connect. If I put my hands together, I'm connecting this hand to this hand because they're different. But I'm not connecting me because I'm still me. So you can only connect that which is heterogeneous. And so those are the things, ladies and gentlemen, that keep me awake at night. The next one we're going to look at is multiplicity. And multiplicity, I think it was beautiful to see the multiplicity work in Professor Suzuki's presentation, where he was showing how there were these multiples, and that was the problem initially, is there's too much. When you have too much multiple, it's called noise. And so what he needed to do is to strip away those multiples until in that slide that I found so beautiful, two important pieces, the two lesions remain. But what we also know is that often, such as in a conference, the multiple actually is the unit. There are many solutions to a simple problem. Now, I think it's called acalculic. That means I do not do mathematics, which must be interesting for you computer scientists to know that somebody has been able to go through 62 years of life without ever solving for X. But what I do know from mathematics is that if you're trying to solve for X, in my experience, there are 5 or 6 different ways to get to the wrong answer. Because I tried them all at high school. I would try this way and it would be wrong. I would try that way, it would be wrong. So the multiple becomes the unit. And it's something that I found fascinating right in this current 21st century thing where we are now, that there was so much discussion at my institution about whether we're going to standardize on Zoom or on Teams or on Skype or on Google. And I then threw my hands in the air and I said, guys, the multiple is the unit. You cannot standardize on one or the other. You have to realize that they are all there. And we have to develop capacity to be able to absorb and integrate all of them. It's the same as motor cars. We do not standardize on one motor car. We take the one that's most appropriate at the time. And so if you look at the multiple of our connectivity, then that is the unit. It comes together inside our machine, but the multiple still remains the unit. And so I'm going to see if it drew me a nice one about multiplicity. That was a signifying rupture. That's cartography. Where did I put multiplicity? It's decalcomania. Nope. I've got multiplicity somewhere. Okay, I didn't do you multiplicity clearly. So we'll go for, I've done multiplicity. So then we need to go to the next one, which is a signifying rupture. A signifying rupture means that with a plant, if you have a plant like a mushroom or a ginger plant or something like that, I know this because in South Africa we have plants called clivias that are very famous, and my wife has animals called dogs. And those of you who are familiar with dogs will know that dogs and plants do not go well together. Dogs tend to break plants when they play in the garden. And what is nice about rhizonomic plants is when the dogs have broken those plants, I can take the two pieces and stick them back in the ground and both of them grow. And so multiplicity gets created by breaking off the pieces and by making that rupture happen. So a signifying rupture means we break things off and we plant them, and that creates new meaning. And again, in our conversation with Professor Suzuki, we saw exactly that. I would never understand the algorithms underneath all of them, but I took away something broke off that presentation for me in that beautiful word graph with all those overlying words, and they stripped down brackets, and there suddenly a piece broke off that is of huge meaning to me. And and I'm going to use going forward. But there are all sorts of other things that broke off for you that you're going to use. And you're saying, okay, if the AI can discover this pattern, then what other patterns can I start using? And then immediately the A signifying rupture is beginning to happen. You please, somebody put into the time, how much time the old professor has left. We have, the good news for you is we have only two more things to look at. And the next one is cartography. Now, I must tell you about cartographies. When I was little at primary school, we were taught about critical thinking. And critical thinking was, as you know, critical thinking for primary school children means you must think like your teacher wants you to think. Then you're a critical thinker. And so we were taught things like we were given a table, 10 more minutes, please. I can do exactly that. So that takes us to the bottom of the hour. I can do that. So, oh dear, I've gone offline. I'll just rewind a bit. Good gracious. Oh yes. So we had this table, and the table in my country was about imperialism versus nationalism. And this was the 1950s. It was just after the war. So nationalism was good and imperialism was bad. And we had to know about who the people were. For us, it was Cecil John Rhodes was the imperialist. Paul Kruger was the nationalist. And we had to learn this. Then when I came to high school, they said, no, you have, the world is a branching tree. You have a sentence, and the sentence has a subject and a predicate, and the predicate has a noun and a verb, and so it carries on. And then when I started teaching as a lecturer, I discovered the concept of the mind map of what was his name? Tony Buzan and mind maps. And I thought this is brilliant because you can put anything. What I really loved about mind maps is that they exploited a piece of my mind that annoyed me, which is when you're sitting in an exam and they ask a question and you know the answer is in the bottom left-hand corner of the page, somewhere in the middle of the textbook. But for the life of you, you can't remember what was written on the bottom left-hand corner of the page. And so that's why this mind map became very exciting for me, because it allowed me to put information at places where I would remember it. And so instead of doing bulleted lists, which, you know, the good thing about a bulleted list is when you put that up, people jot it down. And so it looks as if they're interested in what you're doing. Of course, they're not interested at all. They've been programmed that if there are bulleted lists, you've got to copy them down. So it makes you feel really good as a speaker, so you make bulleted lists. I thought, no, this doesn't work. I should rather use mind maps. And so I would draw a map on the board. I would put the heading of the topic in the middle, and I'd really take the paragraphs headings and put them on the sides, and then I'd refine it and refine it and refine it. And there would be a mind map for the kids or for the learners. And then I discovered that when I looked around, they had all copied down my map. And so here's the problem. I had a map because I made the map. They all had tracings of my map. And that makes no sense. They should have maps, not tracings, because every one of us makes our own map. And so I'll quickly just go to cartography. There's the cartographies. And it's interesting. This is just AI that drew these pictures, by the way. I just typed into openai.com, draw me a picture of cartography. And look what it does. It gives me an old-fashioned map, then it gives me a regular map, and then it gives me people standing in relationship to one another. And that's what cartography is about. Cartography is about plotting the relationships between things. And therefore, each of us should be drawing our own map. And that's the joy of a cartography. It's how we draw our own map. And so how I did that in my teaching is that I don't get my students to put the heading in the middle. I get them to put their own photograph in the middle. And then they've got to link to things that they believe is important to them. So I would put myself in, let's talk about town planning. I would put myself in the middle, and now we're talking about planning of towns. So one thing we would look at would be urban or rural. Is it a big city or is it a small town? In my own case, it would be rural. I live in a very small town, about 500 houses, but I'm about 20 minutes from a big city. So there's the tension between the two. So I would draw that on my map. Then we could look at services, and we could say, well, services would be street lighting. Do we have street lighting? Well, in the entire city, we have street lighting, except in my village. Why? Because we are poor? No, because we are rich. We can afford our own lighting, solar lights that switch on and off only when required. And we like to see the dark at night. And so now can you see that my cartography and the cartography of the poor people who live 3 kilometers away from me is two completely different cartographies. I don't have street lighting because I have money to pay for light. They don't have street lighting because they don't have money to pay for light. So their cartography, their map, and my map of the same subject, town and regional planning, is a completely different map. And then the last one I want to look at, I'm hoping that you've voted now already, that you've got your connection, heterogeneity, multiplicity, rupture, and cartography, which means we draw our own maps. And it's been really interesting for me to go back in my own research trajectory. I've been told that I must get re-rated as a scientist, and I've got a week in which to write up my entire research history for the past 8 years. And to look at that map is fascinating to me. So, and then the last one I want to look at is my favorite word in the whole world, and that is called decalcomania. Now, decals, we all know, decals are tiny little pieces of paper or degradable material that have designs on them. And then you put water on that and you put it on your hand, and it transfers the picture from the paper onto your hand or onto your bathroom tiles or onto your fancy cups and saucers or so. They're all little patterns that you can apply somewhere, and then you can take patterns and make patterns of the patterns. And so when I asked him to draw me decalcomania, that's what I got. So there's the pattern. Can you see how the pattern is repeating on this strange little animal? He's got those little ribs at the back, and then they come across, and you've got the little ribs at the back and so on. But what's also fun is if you just type into Google just the word decalcomania, and you can see I've done it so often already, and you do an image search, there's what you get. And these are the ones that we remember as kids, the little ink blots. And there you can see another one. And they're all just endlessly repeating patterns that just go on and on and on. I'm going to show you the one, if I can find the Singer sewing machine at the bottom here. There we go. Here you can see how decals are used. There's one leaf, and there we put the other leaf. And we simply put these little decals on and we stick them down. But here you can see these endlessly repeating patterns. And to me, that is the essence of education. It's the essence of rhizome theory. It's the essence of science. And again, there I connect so well with Professor Suzuki, is our ability and our desire to recognize endlessly repeating patterns. Where are the patterns? How do we lock into those patterns? Because the aim of education, the aim of theory, and the aim of research is to be able to predict. And to be able to predict, we must be able to recognize those patterns, no matter how difficult they are. And how do we do that? We predict our patterns because they follow our maps, And the maps that we have are each individual maps of ourselves that were created as pieces broke off from somewhere else, and we assimilated that into multiple ways for ourselves that were all different and all connected. And ladies and gentlemen, that then, with a few minutes to spare, is my little bit on rhizome theory and how I think the world works or doesn't work. And I think I've stopped maybe a little bit early, so you can ask me one more question. And that is it. And now what I'd like you to do is click on the vote button, the submit button at the bottom. And while you do that, I'm going to open this. And you can see here, I started this little graph in 2014. In September of 2014 is when I started doing this plot. And here you can see what's happening. We're saying all of us believe that we are connected. And I think that with what happened since COVID, we have been more connected than ever before. We still believe in the heterogeneity. We go right down, but cartography is where we're bad, because we still try and batch process. We're still trying to take a batch of first-year students, make them a batch of second-year students, make them a batch of third-year students, and then give them bachelor's degrees. So that's the low one. But what is beginning to happen is, over time, is that we are really interested in the decalcomania. And so let me go to the meeting controls, stop sharing, keep on the sharing because I might want to show you other things, and look at the chat to see if there are any questions in the chat. And now it's all terribly quiet.
Okay. Okay. Thank you, Professor Cronjé, for the marvelous exposition. Maybe I'd say it's very well. If you say Suzuki was mind-boggling, I say yours is very mind-opening, perhaps. Okay, and it's a very interesting, but in the opening, how you say how the world is took a comeback to us with just one tiny thing, the COVID-19 virus. I saw once a meme that says that this pandemic is the way the earth came back to us for what we have been doing for many decades previously, the pollution and the industrialization and whatever things we do to Mother Earth, and this is how she returns to us.
Yes, yes, yes.
Okay, so here maybe we will try to take some questions from the audience for your presentation.
Right.
If you don't mind, I would like
Yes.
to invite. Yes, if any participants have any questions, you can type in the chat box. Or
Thanks. I see Jos has already asked me one, and I'm so glad that you do, because this is a fascinating study for me as a professor of education. He says, just curious, since you use the tools, what's your opinion on AI generated images such as DALL-E and Stable Diffusion? We used to believe that art is the bold line that differs the human from the robot. How do we treat this advancement? And how should we define our creativity in the future? I think what I showed you, let's go back there. We as human beings are still the creators, or we are still the critiques of this. I couldn't decide on one of the three because I wanted to show you all three. And so my contribution then is that I generated these images and I selected them. And that's always been. Now, you will remember when you were a small person, you would go to the supermarket, you would get a project that you must bring pictures of ice cream. And your parents were furious because now they had to spend their whole Sunday night looking for pictures of ice cream. and cut them out, and you had to stick them in your book, and so on. And this is just the same. It's just that I don't have to tear out somebody else's book, and this is not my own original art. But what it does do is it's my selection. So I'm the curator of this, and I'm beginning to think. I've actually written a little blog post on a thing that I call collectionism, not collectivism, but collectionism, which means that we as human beings make collections around us. And as we go along, so we grow those collections, and then we diminish those collections. Sometimes we swap things, sometimes we keep things in. And so, I mean, I was horrified the other day when let's do this quickly. I actually set this up. I've got writer on. Can you still see my screen, by the way?
Yes.
So to yours, I've got writer on, and I'm asking it to write to me about connectedness in rhizome theory. And let's see what it tells us. So it's writing for us. And pretty soon we're going to know everything. The rhizome is a metaphor of a non-hierarchical and non-linear interconnectedness. It's an idea that was first introduced by Deleuze and Guattari in their book 1,000 Plateaus. It's an alternative to the street structure of traditional linear thinking, which they believe is too rigid and too limited. The idea of rhizomes has been widely accepted in many different fields, including philosophy, science, architecture, and art. There it is. I couldn't have said it better. So, Jos, the answer is, in academia, we are going to have to start thinking very much the way Professor Suzuki is thinking. We're not opposing the machine. We're teaching the machine to do what we want it to do. And the machine has now given me a first paragraph that I would have been able to write myself. I will put it through Turnitin to make sure the machine did actually generate it itself and didn't just cut it from Wikipedia, because it looks very close like Wikipedia. But if I'm going to take this from the machine, I've got to do two things. I've got to credit the machine. And this is, Professor Suzuki did that very nicely. He said, this is my machine, this is its name, and this is what it does. And so I should be able to credit the machine and say, this is how I got the rhizome. And this piece was written for me by writer. And this is where we're going to go further. We can't ignore it because it's there, and it's a very, very useful tool. But we have to use it carefully. You can't just get it to write you the whole thing and submit it, because then you're lying. More questions?
Thank you very much, Professor Cronjé, for the explanation. Maybe perhaps there are the questions from the other participants. Or Pak Jos, are you satisfied with the explanation?
I think one of the issue is you said that we are not supposed to oppose the AI advancement, and I agree on that. But in most cases, we are forced to oppose them. For example, I read an article about a few weeks ago. There's an art competition held by some institution, and the winner is suspected to be generated by AI, and the whole art community is a little bit confused about that. How we draw the line of that? I mean, of course, the winner agreed that he performed some modification, but mostly generated by AI. So my question is, you said that we're supposed to accept the advancement. Most of the time, there's so many conditions that we are forced to against it. What do you think about that?
I love it. And I think, Jos, it talks to me of multiplicity. This is yet another input. You and I are too young, both you and I are too young to remember when Jackson Pollock came onto the art scene and started making things. Jackson Pollock. And so here was Jackson Pollock, and that's the art he made. And when Jackson Pollock first started making these things, people said, but this is rubbish. My grandchild can make this. And of course, Jackson Pollock's answer was, but he didn't, did he? And Jackson Pollock is one of the most famous, one of the wealthiest artists there's ever been for doing things that, which essentially, technically, you could call rubbish. And yet he becomes internationally famous. Now, AI is not better or worse than Jackson Pollock. AI is yet another creator of visual input. And where I think AI is going to really hit us very, very hard is in the domain of accessible art. So if you open a hotel and you need 500 images because you've got 500 bedrooms, you are now no longer going to commission a local artist to make you 500 paintings. You are going to generate 500 images, stick them on your wall. But what did you use previously? You used the cheapest artist you could find. What you had on your wall was not art, it was pictures. So the question, I think, again, the question is that it lies with our interpretation. It's what is the value? Because if you buy a Van Gogh, you're buying somebody's really bad pictures of sunflowers that don't even look like sunflowers, and I can have them drawn much more prettily by AI. But that's not what I'm buying. I'm buying the anguish of the man who cut his ear off. And that's worth millions. So it's the backstory, it's how you wrap it. It's the whole thing. What the AI makes is and let's take that back to Professor Suzuki's. He's made a machine that can see things that are interesting. The value of his machine is that he's saving lives. And so we need to look at what the value is and where we find that value statement. Hey, this is fun for a Tuesday morning.
Okay, thank you very much, Professor Cronjé. So I see it's what you explain is we cannot ignore the context or, as you said, the background story, and which in the end it's how things are related to one another. It's the rhizome of things, perhaps, that what makes it different. That's what makes it beautiful or ugly or scary or whatever.
Exactly.
It's how it relates to how it relates to the other stuff or the other concepts or the other events, perhaps not by what it is on itself. Something like that, Professor Cronjé, from what I get.
I must show you a thing that I made that might help you in that. Oh dear, now it's gone away. Let me find it again. I'll just put it on my screen for you. So this is a student of mine who took my rhizome theory. It took a little paper that I wrote. I might send you the link later. So he had to make an analysis of a social network, and he had to look at people, purpose, policies, and computer systems. And so under connectedness, he looked at what he could then write in there. He could analyze this whole community by saying, what are the people? How are they connected? What is the purpose of their connections? What are the power struggles within those connections? And how do computer systems help or hinder them? Then he looked at the heterogeneity. How were those people different? What was the purpose? How did they use those differences to get to themselves, et cetera, et cetera? So this would become a very useful tool with which you can then analyze any product, anything, to get to what you're saying, Professor Amir, about the context. This little tool that my student made gives us a very valuable type of context.
Okay, thank you, Professor Cronjé. This is all this is very interesting, and that is something I think all of us tend to take for granted, but we never really take the time to look into it more deeply. Unlike you, who these things kept you awake at night. For most of us, this thing just put us more deeply in our sleep. Yeah. Okay, and perhaps I would like if there are other participants who would like to maybe have some ideas or some questions for our Professor Cronjé, you may ask him directly or type through the chat. It's okay, whichever works.
I'll just put in the chat a little a link to the paper I wrote on which this document is based, about how when the virus sent us all apart, how WhatsApp brought us very close together, as that tension between being forced apart and brought together by WhatsApp and this document. So I just shared that for you. If anybody's interested in reading it, it's in the chat.
Okay, thank you very much, Professor Cronjé, for the share. I believe this would be very beneficial for us to contemplate on. One moment. Okay, it seems that time is. Unfortunately, time again is what set us. But I still enjoy your presentation very much, and I would really love to be in your classroom. Maybe sometime it would be very fascinating. I believe to follow one or two of your class. Very mind-opening, I think. Okay.
Thank you.
So before we part, allow us from the committee to present you with a certificate for your wonderful presentation today. Please give us a moment. So there you are, Professor Cronjé. Please accept this certificate as a token of our appreciation for your wonderful presentation today, entitled A Post-Human Look at Post-Pandemic Research in the 6th International Conference on Computing and Applied Informatics, ICCAI 2022, A New World of Research, Sustainable Research in a Digital World. This certificate is presented to you from Dr. Maya Sylvie Lydia, BSc, MSc, who is the Dean of our Faculty of Computer Science and Information Technology, and also from Professor Dr. Poppy Ezi Hasibuan, who is the Vice Rector of Research, Community Services and Corporation of Universitas Sumatera Utara. We really all thank you for the wonderful presentation and for the wonderful material that you help us to open our minds more wide. And we hope next time we can have you present physically here in Medan, Sumatera Utara. Okay.
Thank you.
Thank you, Professor Cronjé, for the time and the presentation. I will give back the floor to the Masters of Ceremony. I'll see you again in the future, I hope, Professor Cronjé. Thank you very much.
Thank you, Mr. Johannes for your outstanding insight, and Mr. Amer Sharif for your help to organize this session. Ladies and gentlemen, we have reached the break session for our main event. The next event is parallel session, where we invite our presenters to present their work. Detailed schedules are available on our website.
We kindly invite all the participants to join this virtual meeting again on 1 p.m. During the break, we will keep the chat open. Should you have questions or requests for a parallel session, feel free to put it on the chat box, and one of the committees would be happy to fulfill your request.